Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will talk about the simplest neutral object, dipoles. Dipoles are formed by a positively charged particle and a negatively charged particle that they stick together. We will first understand qualitatively their motion and how they interact with each other and how they are formed. Then we will understand what dipole moment is, a very important quantity when analyzing situations with dipoles. And finally, we will see how dipoles behave in an electric field. So, let's start! Great, let's do a qualitative analysis of dipoles. Dipoles are formed by a positively charged particle and a negatively charged particle. And remember from the past video that these particles have electric field lines joining them in this direction, and they have also electric field lines going outside of them. Alright, now when we have, for example, let's understand what happens when we have four particles.
If we have a negatively charged over here, another negatively charged over here, a positively charged particle around here, and a positively charged particle right around here,
they will quickly attract together to form two dipoles. So we will have over here
a positive and a positive, and over here a negative and a negative.
We will have two dipoles. Now, dipoles tend to, because they are neutral, but they still experience the electric field and they still make a little bit of electric field that falls off very quickly. It could be calculated that it falls off such as 1 over r to the cube. So it's a very weak electric field. Now, they will tend to align to each other so that this positive charge faces that negative charge. Therefore, this process will happen very quickly. Then, much more slowly, these dipoles will tend to align to each other.
So we'll have a positive here, and a negative here, and a negative here.
What is really happening is that these lines that are going up into space are being of this dipole are being received by these lines that come to the negative charge of this dipole. And then really slowly, this is going to go, and the dipoles are going to become closer and closer together until we have a four pole, or I don't know how to call this because it's quite a strange object formed over here. So this is more or less the qualitative analysis of how the dipoles behave. However, we still need to know a very important question, and that is how they turn. What is the torque that they experience due to an electric field? And we will answer that in the next two segments. Great, let's introduce dipole moment. When we have a positively charged particle and a negatively charged particle, a very important quantity to analyze this situation, or in general when we have a neutral object that has different particles, is dipole moment. That also extends to more particles, as we will see. Let's set this up in a reference frame. Let's call this the I hat vector, the j hat vector, and let's say that both particles are the same distance a from the x-axis. We are going to define dipole moment, which is going to be represented with a p as r1 times q1 plus R2 times Q2. Therefore, let's denote this as 1 and this as 2. In this case, let's this particle have charge Q and let's this one have charge minus Q. We will have that the dipole moment is, let's see, R1, which is, well, that seems like a 2, but it's really a 1. R1 is going to be pointing up, A times I hat, times a positive charge, so just Q, and R2 is going to have minus A I hat times minus Q. So we see that these two minus signs cancel, and we're going to have the dipole moment is 2AQ in the I hat direction. It's very important to note that in general, the dipole moment will be pointing from the negative charge to the positive charge. It can be proven, and it is left as an exercise to the viewer, that dipole moments can be extended to more groups of particles by the principle of superposition. However, we first need to define the dipole moment in a more precise way. In general, when we have multiple particles, we are going to define dipole moment as the sum over Qj times Rj. Well, this is a vector. And this will be our definition of dipole moment in general. And this is pretty analogous, and it remembers a lot to the definition of center of mass. And there is something pretty curious about it. Now, you could think, well, if dipole moment is that important to dipole interactions with electric fields, it shouldn't be dependent on our origin or our reference frame. And we will see that it's really not. If we define another reference frame right around here, S, we can define the units vectors that are in our situation as ROS and RS2, with this being R2. In general, this can be carried out to any number of particles, and this is what we will do. But it's very important to note that R2 is going to be equal to ROS plus RS2, which in general means that Rj equals ROS plus RSJ. Now, what happens if we substitute this expression for J in here? We're going to have that P, this expression, it's going to be the sum over J of Qj times ROS plus RSJ. And we are going to have this, we're going to divide it in two sums. This is sum over Qj times ROS plus the sum over J of Qj times RSJ. We could denote this as P sub 0 because it's on the origin, on our original reference frame, and this is no other thing than P on our S frame. But now something very important in here. In here we are summing over all different charges. And a very important thing about dipole moment is that it is only relevant, or it only exists really, when the object is neutral. If it's a charged object, dipole moment doesn't have really a definition. Therefore, this is going to be defined by, by definition 0. In that way, we find that dipole moment is really independent of the reference frame we are using, as we have found that these two dipole moments are really the same thing. Great! Now let's try to understand how our particle behaves in a constant electric field. If we have our dipole with a positively charged particle and a negatively charged particle, and we have a constant electric field, for example, in this direction, the positively charged particle is going to experience a force in this direction, and the negatively charged particle is going to experience a force in this direction. They are kind of joined by the electrical interaction. Therefore, we see that this dipole is going to rotate. However, we want to know the torque that it is experiencing. Recall that in general, torque is defined to be R cross the force that is being experienced. And in this case, the total torque is going to be a sum over J of each of our individual particles cross the force that they feel. And each of our particles is going to feel a force that is going to be related to this external field, that is going to be constant. Therefore, this is going to be equal to the sum over Rj over J of Qj times the electric field, the constant electric field it is experiencing. Now, as Qj is not a vector, it can go through the cross product and get to this side. And we get that this is the sum over J of Qj times Rj cross E. However, E doesn't depend, the electric field doesn't depend on the sum of J. So we can restrict the sum to be around this by taking the common product E out of it. And then, if you recall from the previous segment, this is no other thing than the electrical dipole moment. And therefore, we see that the torque that a dipole experiences is proportional to the electric field and to the dipole moment of the particle. That is all for today. I hope you understood all of these different things about dipoles, because they are very important as they are the simplest neutral object in our universe. I hope you liked it, and any doubts left you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!